Alright, so today we're going to continue on with section 12.5, and we're going to delve a little bit deeper into these complex numbers, and we're going to look at powers and roots of complex numbers. So we want to understand how to find powers and roots of complex numbers. We're going to be using DeMoivre's theorem for that, and that will make that process very simple. So first we want to think about our trig representation of a complex number. So we know if I have some complex number z, I can write this as r times the cosine theta plus I sine theta, or we can write this as z equals r cosine theta plus r I sine theta, and this z is from, if we have some z equals a plus bi. So now I know we learned yesterday how to do multiplication with complex numbers, but I want you to actually find z squared by multiplying them together, so not using the shortcut that we learned yesterday, just to kind of see how it works. Also, when you're doing that, I want you to find z squared for the standard form and compare that to what you get in trig form. So pause the video, multiply those out, unpause when you're ready to check your work, or if you're confused on what I'm asking. Okay, so none of this should be new, but in standard form, if I have z equals a plus bi and I square that, sorry, I forgot to write squared here, so z squared is a plus bi times a plus bi, which is a squared plus 2abi plus b squared I squared. I squared is negative 1, so the real component becomes a squared minus b squared, and the imaginary component becomes 2abi. So it's not too bad when it's squared if I'm in standard form. It's a little bit of work, but not terrible. And then remember, I know a is r cosine theta and b is r sine theta. So when I compare that to my trig form in the end, we can see where these relationships come from. Okay, well, what if I am in trig form? So z squared is r cosine theta plus ri sine theta times r cosine theta plus ri sine theta. Multiply this out, and we end up with r squared cosine squared theta plus 2r squared I cosine theta sine theta plus r squared I squared sine squared theta. I squared is negative 1. Every term has an r squared, so I factored out the r squared. And so then here I was left with cosine squared theta, and then this became a minus sine squared theta. So I have cosine squared theta minus sine squared theta. And then here I factored out the r squared, so I was left with 2I cosine theta sine theta. I rewrote that as I 2 sine theta cosine theta. Cosine squared theta minus sine squared theta is cosine 2 theta. 2 sine theta cosine theta is sine of 2 theta. Those are my double angle identities. So z squared is r squared times cosine 2 theta plus I sine 2 theta. Now again, we knew that from what we learned yesterday, that when we multiply two complex numbers in trig form, you multiply the r values and you add the theta values. So if I'm multiplying, or if I'm squaring something, then I just multiply r by itself, so it becomes r squared, and I add the theta values, so it became 2 theta. So then if I asked you what about z cubed, well, at this point now, if you actually had to multiply these out, then you would start to see that this is going to become a little bit more of a pain, especially if it's in standard form. If it's not in standard form, if it's in trig form, then you should be able to understand, okay, well, if z squared is this, then z cubed would be z squared times z. So I can use that property again. So I would know that z cubed would be r cubed cosine 3 theta plus I sine 3 theta, and so on from there. And so the point is that in general, one thing DeMoivre tells us is that if I have a plus bi to the nth power, and I write this in trig form, it's z to the n is r to the n times the cosine of n times theta plus I times sine of n times theta. Or z to the n is r to the n cis of n theta. So it's a nice generality that we can use, and we can easily see where it comes from as well, as opposed to having to continue to multiply these out. we can understand what that pattern is going to be. So let's do an example. So I want you to evaluate this power, and I want you to write your answer in standard form. So pause the video, evaluate the power, write it in standard form, unpause when you're ready to check your work. Okay, so in standard form, we should end up with negative 81 over 2 minus 81 root 3 over 2i. How do we come up with that? Well, first we use DeMoivre's theorem, so this becomes 3 to the 4th times cosine of 4 times 330 plus I sine of 4 times 330. 4 times 330 is 1320, 3 to the 4th is 81. Now here, just to simplify things for myself, I recognize that 240 degrees is a coterminal angle of 1320 degrees. So if I evaluate the cosine of 240 and the sine of 240, that's the same as evaluating the sine of 1320 and the cosine of 1320. The cosine of 240 is negative 1/2, the sine of 240 is negative root 3 over 2. Distribute the 81, bam, got my answer. Next, evaluate and write your answer in standard form. Negative root 2 over 2 plus I times root 2 over 2 to the 12th. Pause the video. Unpause when you're ready to check your work. Okay, so here we should get negative 1 as an answer. When you first look at this, probably don't think that you're going to get negative 1. Who knows? Maybe you did. I don't know. Alright, so here I'm given the original complex number in standard form. So I need to find r, so the square root of a squared plus b squared, and I get 1. And then I need to find theta as well. So remember, tangent of theta is b over a, and b over a is negative 1. Now here I have to actually think about this complex number and recognize that it's going to be in quadrant 2. I know it's in quadrant 2 because a is negative and b is positive. So theta in this case is actually going to be the angle in quadrant 2 where tangent is going to equal negative 1, and that's 135 degrees. So if I call this complex number a, then, sorry, that's a bad labeling, shouldn't have that there. So I can say z is 1 times cosine of 135 plus I sine of 135. So then z to the 12th is 1 to the 12th times cosine of 12 times 135 plus I sine of 12 times 135. 1 to the 12th is 1. 12 times 135 is 1620. A coterminal angle of 1620 is 180. The cosine of 180 is negative 1. The sine of 180 is 0. So that's why the I term goes away. Alright. Hopefully you're getting the hang of that. Moving on. So, little review. I want you to pause the video for a minute and solve for x in each one of these scenarios. So find x when sine of 4x equals 1/2. Find x when x cubed equals 27. And find x when x squared plus 64 equals 0. And let me specify a little bit more for this one. We want our answers to all be between 0 and 2 pi for number 1. Pause the video, solve those, unpause when you're ready to check your work. Okay, so if we look at number 1 here, we should end up with pi 24s, 5 pi 24s, 13 pi 24s, 17 pi 24s, 25 pi 24s, 29 pi 24s, 37 pi 24s, and 41 pi 24s as our answers for x. How do we come up with that? Well, remember, because this is 4x and I want my answers between 0 and 2 pi, I actually need to originally go around the circle 4 times and then divide all those answers by 4. So first, between 0 and 2 pi, where does sine equal 1/2? Well, that's at pi 6 and 5 pi 6. Then I find coterminal angles of each of those, so 13 pi 6 and 17 pi 6. Coterminal angles again, 25 pi 6 and 29 pi 6. And then one more time, 37 pi 6 and 41 pi 6. Divide each of those answers by 4, and I get all of my values of x. Number 2. So hopefully you didn't just take the cube root of both sides, because then you probably only got one answer. But in this case, we want to subtract the 27. This is the difference of cubes. Factor that, x minus 3 times x squared plus 3x plus 9. Set each factor equal to 0, x minus 3 equals 0. Sorry, I circled prematurely. Our answer is actually x equals equals 3, not x minus 3 equals 0. That's my answer. Well, that just made a mess of things. So, let's see, just a little touch up, and you never knew anything was missing. Alright, so we get x equals 3, and then the trinomial is not going to factor, so I chose to complete the square. We know that we are going to get imaginary answers, and I get x equals negative 3 halves plus or minus 3 root 3 halves I. Then for the last one, here we can subtract the 64, take the square root, and we get x equals plus or minus 8i. So why did we do this? Well, this leads us to roots of complex numbers. So if we are going to take the root of a complex number, again starting with a plus bi, so we could write that as r times cosine theta plus I sine theta. We know from DeMoivre's theorem how to find powers of the complex number. Well, roots is very similar. So if we want to find the root, z to the 1 over n, this is going to be r to the 1 over n times cosine of theta plus 360 times k over n plus I times sine of theta plus 360 times k over n. Well, what is k? So k is telling us how many roots we're going to have. And it always just counts from 0 to n minus 1. So actually, I'm sorry, I misspoke. N tells us how many roots we're going to have, because if we are taking the nth root, we will have n distinct roots. So for instance, if we're taking the cube root, then we should have 3 answers. So if we think back to this problem here, if we took the cube root of 27, 27 is a complex number, there should be 3 cube roots of 27. And voila, there were, right? I know. So the k is just going to count each time, starting at 0 and going up to n minus 1. Why does it go up to n minus 1? Because if it went up to n, then you would be at a coterminal angle of the original number. Alright, let's do an example. So if we want to find the cube root of 27, well, first, let's rewrite 27 is in trig form. So 27 is 27 times CIS of 0. So if we use DeMoivre's theorem, we know the cube root of 27 is 27 to the 1/3 times CIS of 0 plus 360 times k over 3. So this leads us to 3 CIS of 0 plus 360 times 0 over 3. 3 CIS of 0 plus 360 times 1 over 3, and 3 CIS of 0 plus 360 times 2 over 3. So then our 3 distinct cube roots are going to be 3 CIS 0, 3 CIS 120, and 3 CIS 240. So these are the 3 cube roots of 27. And if you change those into standard form, you will end up with 3 negative 3 halves plus 3 root 3 over 2i, and negative 3 halves minus 3 root 3 over 2i. So we have one more example. We're running out of time, so I'll preview that for you. I want you to find the 2 square roots of negative 1 plus I root 3. Go ahead and do that, and then on part 2, we'll go through the answer.